Wonderful. Yeah, so thank you so much for giving me the opportunity to talk remotely. Unfortunately, long COVID got me pretty bad, and so I can not really travel. So for the foreseeable future, I will unfortunately have to give talks online. Anyway, I'm really excited to uh, tell you about some recent results. I actually have never talked about these yet and just prepared this quickly over the last few days. So there may be a few missing citations or so. Please excuse me for that. And yeah, and so what I will be talking about mostly is about an experimental dualization of super and subradiance beyond the Dicke limit. And this is actually in our quantum gas microscope. Here's the team. So this is the new quantum gas microscope that we built that is using erbium atoms. This started as an experimental collaboration with the Francesca Felino's group. So the main students doing this work right now are Alec Douglas, Michal Survik, and Lin Su, and then the theory is done together with Oriol, Stefan, and Susanne from which are our theory collaborators at Harvard. Good. So we built a new experiment, an erbium quantum gas microscope, which has some nice features. It can create Bose-Einstein condensates very quickly for rapid experiments, but then most importantly, it can use the magnetic interaction between the erbium atoms to have a dipole-dipole interaction between particles. We're not really using this in the main work I will be talking about today, but this was the motivation. And then in order to maximize the interaction, we have a lattice with a very small lattice spacing of 266 nanometers. That gives us 30 hertz of magnetic interaction between neighboring atoms. We have then also implemented a so-called accordion lattice, where before imaging, we can increase the lattice spacing, and then it's very simple to image every single atom. We just do flash photography. We scatter, the atoms scatter enough photons before they fly away, so that we get a perfect picture, like you can see here, where we can tell pretty much perfectly well on every lattice side whether we have an atom or not. So as I said, normally we use this experiment to do many quantum mechanics at ultra low temperatures, like for example, studying the Bose-Hubbard model that we can now extend to have magnetic dipolar interaction. And for the first time, we have been able to really get this into a regime where the dipole-dipole interaction between the particles becomes the dominant energy scale. And so we observed quantum phase transitions coming from a superfluid into a dipolar quantum solid. Here, for example, if the dipoles are perpendicular to the plane, we get this a checkerboard order at half filling, for example. Or if we align the dipoles into the plane, we get stripes of various directions. And again, these endpoints are classical states, but the exciting thing is that we really can do these quantum phase transitions in this strongly correlated physics that is now really dominated by the long-range dipole-dipole interaction. So if you're interested in that, the paper is at the bottom. But what I will be talking about today mostly is completely different. So we just realized that this experiment where we have this very small spacing lattice and even a lattice where we can change the lattice spacing, this of course is wonderful to create, to really play with a completely new type of quantum optics, where we have arrays of particles in the motional ground state, so they're really their location is really well defined. Right? If they were hot, then they would you would have much more uncertainty. We can prepare these arrays kind of pretty much perfectly by loading the lattice with a cold quantum gas, and then we can study all kind of quantum optics effect in completely new regimes. And what I will be talking about is observing superradiance in subradiance. I'm sure most of you know what this is about. The idea is that if you have multiple emitters, usually within if you have multiple emitters, then they can emit light collectively. This can happen in two ways, right? If you have two emitters that both oscillate in phase, then of course the amount of light that's being emitted is 4 times the intensity of just a single emitter, because you have to add the amplitudes. And if they constructively interfere, if the two emitters are spaced much less than a wavelength, for example, right, then you get 4 times the light. So that leads to a faster decay. And this is called superradiance. And so if you have lots of emitters, like in a dense cloud, for example, within one wavelength, then you get a scaling, or like the decay happens faster by a factor of n. But conversely, you can also have the opposite situation. If two emitters oscillate and they oscillate against each other out of phase, then you get destructive interference. So that means the particles would never decay because there is no light being emitted. So this is the very simple model that you can have for kind of like a quasi-classical system where you have multiple emitters within the same wavelength, or just emitting into the same mode. But of course, this gets much more interesting if you think about that these are really quantum emitters that we put, for example, perfectly into the excited state. This has, of course, been extensively studied in the Dicke limit, meaning you couple to one mode, right? If you have, you can do this in vapors, in dense vapors with many particles per lambda cube, or you can do it with optical cavity, where you pick out one mode that you couple to. Right? But what I will be talking about today is a very different regime, because we have these nicely arranged arrays of atoms, 100, 200, 500, 1,000 particles with like near perfect grids of particles. But our lattice spacing can be very small, so we can have multiple particles even within that distance. But even if that's not the case, of course, collective effects emerge. And so we have an amazing playground here now where we can study this on a microscopic level in a very, very clean system. Good. So as I said, we can tune our lattice spacing continuously between 266 nanometers and 3 micron. And so on the small end, this is small compared to the 841 nanometer transition that we use. It's an 8 kilohertz byte transition. And we can excite the system from a beam coming from the side. And then if you have it excited, these atoms can now collectively emit photons, and in the process also really change their quantum state, essentially. At the other end of 3 micron spacing, at this point, you can pretty much like collective effects, and so this gives us a reference for just normal spontaneous decay of particles. The beauty is, again, as I said, normally we start with these kind of nice, perfect arrays. And also, as I said, the particles are at the ground state on each lattice side, so the position is really well defined. And once we have prepared a system like that, we can do, for example, a pipe pulse and put the atoms into the excited state, where they can now, where they are ready to emit light. Then we just wait. We can have the physics happen, like superradiance, subradiance, whatever collective effects happen. And then, in contrast to other collective photon emission experiments, we are actually not detecting the photons. What we can directly detect is, for each atom, whether it is still in the excited state or has decayed to the ground state. And that gives us some really nice advantages. For example, we can measure spatial patterns. We can measure correlations between the emitters. We also don't need a very good photon detector that may lose photons and so on. So with very high fidelity, we can test each particle here, whether it has decayed or not. What we do is we move the decayed atoms and then wait until the rest decays, and then we can take a snapshot and tell with near perfect probability what the population is. And if you do this and we just have a look how quickly the particles decay, then we see a very marked superradiance here. The system decays significantly faster. So the yellow dotted line here is the decay of individual particles. It was also confirmed in other measurements at large spacing. And then here these the dots show the significantly faster decay if you have a collective emission at that short lattice spacing. If I zoom out a bit here, you can see that the particles decay. The superradiance, they decay faster than than uncorrelated. And then here at the tail end, you also see that they actually remain excited for significantly longer. And that is subradiance. We can measure from this data. So it's a bit hard to see here, right? Because these exponential curves. What we can do, of course, is at every moment we can measure the slope of this curve, and that gives us the emission rate, like the rate of decay from excited to ground state. And we can then normalize that. We can compare that to the situation where you have just spontaneous decay, which is the yellow line here. And so we can do this with different atom numbers now. If we do it with 200, you see that our emission rate goes significantly above that of normal spontaneous decay, and then it dips below, far below. And we can tune the atom number and see how this effect depends on atom number. And in fact, we see that with the increased atom number here, 350 particles, we get more decay. You can compare this to theory here. It's actually not easy to compute this for this system, but Oriol and Susanne's group and Stefan did a great job, and also Alec on some calculations to measure this decay. And if we keep increasing the particle number, we see a faster and faster subradiant decay. We can plot this maximum decay, or like how much faster it decays compared to normal spontaneous decay as a function of atom number, and we see this nice scaling behavior. Good, so this is superradiance. Let's zoom a little bit into the subradiance here that we see at the bottom, and for that it's better to plot it, of course, on a logarithmic plot. And if you do that, then you see that it's actually quite remarkable as the particles start to decay, they really end up in kind of like a many-body dark state where they all oscillate in a way that they cannot emit more light, or kind of these states kind of, well, the other states decay away and these ones remain essentially, and the system is really then in this kind of, it drives itself into this dark state where the lifetime is nearly an order of magnitude longer than for normal spontaneous decay. And we also measured this as a function of atom number, so there seems to be no big change, but it's also expected because this is more of a local, like a slightly more local effect, essentially, where you create a pattern of excitation that does not couple to light fields, essentially. The cool thing is we can directly image each atom, whether it has decayed or not, and that allows us to measure correlation functions. And so here again is the superradiant decay curve compared to the spontaneous emission, and at different times here we see that this kind of like ferromagnetic behavior emerges, where so red means positively correlated, so if you find the central atom here to have decayed, then these red atoms are more likely to have also decayed, right? And so this really hints at this is a really complex system. You have a lot of particles coupled to a lot of light modes, and the decay now gives rise to this essentially ferromagnetic behavior that is emerging here. At later times, interestingly, in the subradiant part here, then you see that antiferromagnetic behavior. So it completely switches, and in the subradiant part, you see this antiferromagnetic behavior. We did calculations, which is not easy. Like you need to do discrete truncated Wigner approximation for as many particles as we have, or like we can't even do it with as many particles as we have. But these are quite complicated computations, but they do capture this physics quite well. And so, yeah, the comparison looks quite good. There are some little uncertainty about the direction of the quantization axis, which is actually pointing. So the quantization axis is pointing in this direction. Of course, there's by the additional degrees of freedom, you can play with like the quantization axis and how that aligns with respect to the lattice. Good. So let's have a look. What we did so far was kind of the most quantum regime. So you go into the excited state and then you wait for the superradiance to occur. And what you actually expect in this case is that the initial decay rate is just the same as spontaneous rate. And that's exactly what we find. So here's again the decay rate compared to the the orange line, which is uncorrelated decay. It starts at that level, and then we get the superradiant response and the subradiance later on. But of course, we don't have to go all the way up. We can also only send our Bloch vector kind of part way up, which means that there will immediately be an oscillating electric field or electric polarization that will emit immediately. And so as we tilt the Bloch vector lower and lower, we can see indeed that we immediately then start emitting at a much higher rate than spontaneous emission. Of course, here this gets kind of like more and more into this classical limit that you can just understand by the interference of the emitted light fields. But you can also see that really in that kind of quantum limit where you start in the excited state, this is where you get most subradiance. We really have still a lot of population left, but it does not decay away quickly. Whoops. Interestingly, we can also measure the spin manifold, essentially. If you think about it, right, you have n spins, and so you can represent this in an angular momentum, kind of like a big spin, right, with a j and the projection of the spin. And normally in Dicke experiments, you're only on the very left side here in this extremal manifold where j is as large as it can be, right? So that corresponds to having a Bloch vector that has the full length, essentially, right? And then if you have decay here for normal decay effects, you can only move in this direction. But the interesting thing is, in our case, it's different because our spins are not indistinguishable. We can actually, so we couple to different j's in the decay process, right? And the cool thing is that we can measure the j. We can do Bloch rotations of our system and look at the Rabi contrast, and that tells us, like we can topographically measure the angular momentum here. And so here, these states correspond to a shorter Bloch vector where you have less contrast, and here you have a singlet state essentially where like a highly degenerate singlet state with a zero-length Bloch vector essentially. So what happens? How do we move in this manifold? Let's measure that. Let's start with the atom in the all the atoms in the excited state, right? And if you do this, let's start with all the excited state. But the first measurement is with a large spacing lattice, just normal spontaneous decay. And it turns out what you see is you trace this curve here. This point, the tip of this curve, is actually like a maximally mixed state, a maximally which corresponds to kind of a statistical mixture of a lot of Bloch vectors around the origin of the Bloch sphere, right? But if we now do super radiance, then we see that we get this trajectory here, which is more coherent than this statistical mixture. And as we start with on different locations on the Bloch sphere, we can really trace out the trajectory in this spin manifold. Oops, yeah. And it agrees quite nicely with the theory. Of course, in the future, we could even look at individual spins and tomographically measure them. So to really measure the correlations on this level kind of that emerge, not just in population, but also in coherences. And so there will be some very interesting directions to really map that out. And lastly, right, the cool thing is we have this regular array, this regular grid. And the question is, what happens now if I change the spacing in that grid, which I can nicely do with our accordion lattice. And of course, what you would expect is that the coupling to the optical modes depends on that spacing. At some spacings, you very efficiently couple to a particular mode or to a few modes. At other spacings, not so much. And as you vary that, so when you vary that, we actually measure this resonant kind of structure where we see kind of like steep slopes emerging at half a lattice spacing or 0.7 of the lattice spacing. And we can compare that to theory, which agrees quite nicely if we kind of add an additional offset. We don't fully understand this offset, but you can see that the shape actually very nicely matches with the theory. And you get these resonances at the points where you're half a wavelength apart in the straight or the diagonal direction. You can kind of imagine if you go over that process, you're kind of like the emission has a certain cone angle. And then at that point, you get very strong emission because you couple strongly to one mode, and then certain modes disappear. And so because of this, you can really get these geometric resonances and directly observe it. We can scan both X and Y, or we can also just scan one direction. Yeah. Yeah, so I hope you could see how this is kind of this is really fun to do a new kind of quantum optics essentially in these systems where we have these clean emitter arrays. And a nice starting point here was really to do this super and subradiance where we can study the collective emission of particles. But because it's a microscope, we can really map out the emerging correlations in this many-body quantum dynamics, right? And we can also measure the angular momentum manifold directly. In the future, we could even do this on a single particle level with spatial information, and then we can see these geometric resonances and so on. Right, but of course, there's much more to do. For example, we are also planning to use even much more narrow transition and Hertz line width that we have. It even happens to be in the telecom wavelength band. And if we do that, then we get a really interesting regime where suddenly the electric spin-spin interaction in this kind of decay and the magnetic spin-spin interaction is on the same energy level. And even the tunneling of particles happens at the same kind of energy level. And so this way we expect to really engineer very complex many-body quantum systems that couple to the light field also, and so you could you could have a bath, you could drive it into interesting, or if you couple it to zero temperature bath, which is kind of your light field, you could drive it into interesting entangled states and so on. So it's really a whole new playground of quantum optics. Let's see. I do have a bit time left, right? What is? Could you tell me real quick?
10 more minutes.
Okay, perfect. Yeah. Good. Yeah. This is all I wanted to say about super radiance and subradiance. Then let me completely switch gear and just give you a brief update, because there are a lot of exciting things happening with our Fermi-Hubbard quantum simulator. So this is the team. Martin Lebrun is a postdoc, and Muxing Su is the senior grad student. Lev, Anand, the other senior grad students, Yuchi is a new student, and Aaron has joined as a new postdoc, and we collaborate with a lot of theorists on this. So completely different topic, right? Back to ultra low temperature quantum simulation. Fermionic particles on a lattice, right? They are a perfect realization of the famous Fermi-Hubbard model, which is deceivingly simple if you write it down, but actually, as you all know, has a lot of open questions and a lot of very interesting quantum phases. It may even hold the key to things like high temperature superconductivity, pseudo gap physics, all these kind of interesting topics that we want to look into. But let me tell you a bit about how we can extend the Hubbard model in interesting ways. And so one way is to change the lattice geometry, and we can do that and do two different things with that. For example, we can create different lattice structures instead of just boring square lattice. We can do, for example, a triangular lattice, or we even get a bit more fancy and program features that, of course, we can program models that give rise to multi-band models. And so let me just outline two of these things briefly here. With the triangular lattice, we had a bunch of papers recently. So here, the first work is where we continuously tune from a square lattice to a triangular lattice by smoothly turning on this diagonal link in the lattice up to the point where it's completely equal and our geometry is purely triangular, right? In this case, we saw a nice transition from kind of Neal order to something more like 120-degree order. But in this work, we had one surprising observation, and this is if we dope the system, we go away from antiferromagnetic behavior of the system and go into a regime where the nearest neighbor correlations are not antiferromagnetic anymore, but instead they become ferromagnetic. And that was really a bit of a surprise. We then continued in this direction because this is linked to kinetic magnetism. And the idea of that is so normally in a square lattice, normally in a Fermi-Hubbard model, you always have antiferromagnetic behavior because of the super exchange that favors neighboring spins to be in the opposite spin state to minimize their energy. But Nagaoka already pointed out in '66 that the Hubbard model can actually support ferromagnetic physics if you go to infinite U, meaning like you quench the super exchange essentially. And he famously proposed that then a single excess atom or a single hole can turn the whole system ferromagnetic. Of course, a single hole turning the whole system ferromagnetic sounds very much what a theorist would say. For an experimentalist, of course, well, if you're not exactly at infinite U and if you're not exactly at t equals 0, then that wouldn't quite happen like that. But can we see this kind of physics, this Nagaoka physics? And the basic idea why this is, like, why would a single dopant turn the system ferromagnetic? We can actually understand this with quantum interference. If you have a general kind of system with, for example, antiferromagnetic order or disordered or so, if an extra particle wants to, or a hole wants to tunnel here, in this process it actually reshuffles the spins along the path. You can nicely see this with the number puzzle here. If this hole moves, right, it leaves behind the which way information it took, if there's a pattern that it moves in, right? But of course, because there's a bit ray information, different paths don't interfere. So that means a hole or an extra particle cannot minimize its kinetic energy by delocalizing, because different paths are distinguishable. But this, of course, changes fundamentally if a hole or a particle moves on a ferromagnetic background. Then there's no path information encoded in any kind of spin pattern. And so now the particle can delocalize and minimize its energy. So that means for a system with an extra or a missing particle, the ferromagnetic state is preferred, because then that extra particle can delocalize. Can we observe that in the experiment? So for this, we need small doping, right? So we did this, and actually, amazingly, it was actually possible to really observe this in our quantum gas microscope by measuring. So if you can simultaneously measure a spin and charge in the system, then we can look at pictures and measure the spin correlations around the location of a dopant that we find. Because what you would expect, of course, is if this dopant here, if this is surrounded by a ferromagnetic environment, then it can delocalize in this region, and that, of course, is favorable in terms to minimize its kinetic energy. And that's essentially exactly what we found. So this is the correlation function. If we find a dopant in the center, then the magnetic environment around that is more ferromagnetic than it would otherwise be. And so this way, it's possible to kind of image this Nagaoka bubble and study this Nagaoka physics really in a many-body system for the first time. Good. If you want to know more, sorry, this is the paper. The other thing I wanted to briefly mention is multiband physics. We can program a leap lattice like this. This was originally motivated by the structure of qubits, and the interesting thing is you get multiband physics now. And not just multiband, you actually get flat bands, because the p sides here, they give rise to a flat band, since the one-year function here changes sign here. And so what that means is that the tunneling amplitude onto these sides from here and from here cancels essentially. And so that gives rise to a flat band here. Every different phase between these one-year functions has the same energy. And then you still have the other bands linked to the d sides. So how can we do this? We can use our quantum gas microscope in reverse to project light pattern to raise the energy of certain lattice sites. And doing that, we can then create a geometry, like essentially program arbitrary geometries by taking out certain lattice sites and realize this leap lattice, which is now also coupled to a reservoir around it, so we can have a well-defined chemical potential.
Markus, a couple more.
Yeah.
Minutes.
I'm sorry?
Just a couple more minutes, and then maybe.
Okay, perfect. Yeah. And so the first thing we can do here is, like, if you vary this chemical potential, we can see how the different bands fill. And yes, indeed, we can see very nicely how first this lower band fills, then the flat band quite suddenly, and then the upper band. So the red is the flat band filling here, right? This is with low interactions. With high interactions, of course, the system changes completely. Right, but famously, yeah. Okay, let me maybe skip this. And we see antiferromagnetic correlations here in very similar to the square lattice. Okay, but what Lee proposes that essentially you get the system, even for kind of like any other interaction, is actually prone to form a ferromagnetic state. And in addition, there are still antiferromagnetic correlation between the sublattices, and so that gives rise to ferrimagnetism. Can you observe that? Well, what we need to do that is to kind of create a Zeeman field, essentially, and we can do that by just introducing a spin imbalance, the difference between spin up and spin down atoms in the reservoir. And if we do this, and then we look how many particles do we find on the two sublattices, we can measure both this kind of ferromagnetic tendency and the ferrimagnetism. And so as we change this imbalance more and more, we can actually very clearly see that the p sublattice sides have a positive magnetization, whereas the D sides have a negative magnification. If we plot this as a function of how much, of how much field we apply, we can see. So this is for square lattice, and the red one is the p sides, and the D one actually goes the opposite. So the more the more red atoms we put in, the less red atoms we have on the D sides. So this is a clear signature of this kind of ferrimagnetism. The ferrimagnetism is strongest kind of for intermediate interaction, right? In the extrema, you can either understand it just with flat band physics, or here then you regain the antiferromagnetic state, but in between is where you get this ferrimagnetism. Okay. And what we currently work on, so of course the idea is that we want to get even colder, right? Quantum simulation, we really want to do useful quantum simulation where we can find out things that we cannot compute or that are really, really hard to compute. And we really want to be serious about this and get to cold temperature physics. So far, if we compare our quantum simulations to actual materials, then we are still at a few hundred degrees Celsius or like many hundred Kelvin. We need to get, of course, to cryogenic temperatures in that kind of analog material, because then, as we know, there are all these interesting many-body quantum states appearing, like charge density waves, D-wave stripes, and so, strange metal, and so on. And so what we have recently implemented is this kind of old idea to start with a band insulator that we had already showed previously can have very low entropy, but then turn that into a useful state by doubling the number of lattice sites. So we turn a single, like we have a singlet, perfect singlet on a single site, then we split that into a double well, and ultimately the question then is, can we go to a many-body state? And can it be does it only work for undoped or doped and so on? You really can't compute that at this point, so we have to try it. And all I want to say is it seems actually to work amazingly well. And it seems that we can create temperatures that are now in this cryogenic regime, kind of where, like in the analog material, are kind of below, significantly below room temperature. So it seems like we can reduce temperatures by a factor of a few, and that is, of course, opens a whole lot of doors, because now we're deeply in a regime that is extremely difficult or impossible to compute. Good. With that, I would like to thank all the team and every single one of the amazing grad students and postdoc working on this. I would like to thank the funding agencies, and thank you very much for your attention.
Questions? Anna?
Hi, Markus. Thanks so much for these super cool results. I'm really excited that you get to see such a clearly the burst. As I have a couple of questions. The first one is, do you have any results about the scaling of the burst with system size, with particle number?
Yeah, exactly. So this was actually this slice here. So give me 1 second. No. Right, so that is, I believe, what you're asking, right? So this is the super radiant burst here, and in this graph we show the size of the burst versus atom number, and it actually looks the scaling looks very clean.
So, and do you know what's that's the scaling? No, not really. So this is it's the maximum derivative. But this is
so maximum derivative means maximum rate. How much? So there are different ways. Actually, in the paper we will show it in different ways. This just means how much higher is the emission rate than you would have if you just did spontaneous decay.
Okay. Cool. Yeah. Sorry, I missed that. And then the second question is more about technical aspects. So, is this a closed transition? How good is your pi pulse, and along what direction lies your quantization axis?
Yeah, right. So it's a fairly close transition. That's good. And the orientation. So this is measured 2D correlations, right? And the quantization axis is in this plane, and it's actually the funny thing is for us, it's a little hard to measure what direction the magnetic field actually points inside the vacuum chamber. But from these plots here, we infer the angle of that. Can you see my cursor?
Yeah.
Exactly. So this would be the quantization axis.
On the plane of the array, basically.
Mm-hmm.
Uh-huh. And do you have any estimate of how good is your pi pulse, your inversion?
That can be very good, like
Okay.
yeah, 99. Because before that we did work on squeezing and got a substantial squeezing using the magnetic interaction. Didn't have time to talk about that today, but and so there we were characterizing those things quite well.
Thank you so much.
Hi. Very nice results. I have a question about the measurement of J. When you measure J, you measure in the frame of the laser, right? You have a phase factor on every atom. And so
that's right.
when you start fully inverted, do you have any reason to believe that super radiance will give you a J in that frame?
Let's see. So yeah. Goes here. Exactly. So this manifold depends on the direction of the excitation laser, right? Mm-hmm. And the Dicke manifold is not unique, of course. If you only have one mode, right, then that's clearly the one Dicke manifold you have. And here we, sorry, and the question was what? So if all the,
exactly. So if you initialize like at the middle of the Bloch sphere, then for sure your J will be in the frame of the laser because you give a phase factor to the atoms. But now
exactly,
if
that's why we started.
There is no reason to believe that super radiance should take you in the right frame. For instance, if you put your laser perpendicular to the plane, I'm sure you would see something different, right?
Yeah, exactly. So these plots do depend, indeed. That's a very good point. They do depend on what axis you choose, or what is the laser direction in which you are probing, right? And yes, so these paths are not unique, right? Like you can choose that arbitrarily. What you can see here is that it is the same basis that is also used to excite, because if you do a partial excitation, we do start on the left here in the Dicke manifold, essentially. Right? If, of course, you have different beam for this analysis or different basis for the analysis, then these points would not lie here anymore in the Dicke manifold. They may be somewhere else, right? But of course, the fully inverted one, of course, is always this unique point. And then yes, and then this decay, how it exactly goes, may depend on the.
So my question is basically super radiance occurs in plane, right? The photons are mostly emitted in the plane in which the laser propagates.
So it depends on spacing and so on, and we actually have to study that more carefully and think a bit more about that. The funny thing is that since we didn't really detect the photons, so we have to look more into that. So depending on the spacing, there are different modes in different directions. In general, it can go, right? If you have emission in phase, then you go a lot perpendicular. But if it's commensurate with some spacing in the plane, then it would be in the plane. Correct.
That's clear. Thank you very much.
Hi. Thanks for a nice talk. When you mentioned the beyond the Lamb-Dicke limit, you're talking about the interatomic separation, right? So what's the size of each atomic wave packet relative to, let's say, being sub-wavelength? And have you considered, going towards larger wave packets and exploring the coupled quantized center of mass and super radiance dynamics?
We have not. I mean, so first of all, what's nice is that we started the motional ground state, so we don't have, kind of randomness in position. It's really in the each atom is in the motional ground state, and then the fraction of like the size of the wave packet compared to the lattice spacing is just given by the lattice depth in E recoil, right? So typically that's a few percent of this of the spacing, or 10 or a few 10% or so, right? And you can tune that by changing the lattice depth within bounds. Again, in E recoil that determines that ratio. Of course, for our bigger lattice spacings, then that extent also gets bigger. And are you thinking about that there may actually be interesting effects if the atoms are delocalized over larger?
Yeah.
Interesting. Yeah, I haven't even thought about it from that, and that would be interesting. We would love to learn more about that. Yeah.
Okay, thanks.
Hi, Markus. Thank you for your talk. So you showed a pattern of the excitation, like of the atoms, in the super-radiant and sub-radiant ones. So do you see any like scale of variations? Like when you say antiferromagnetic, does it mean lattice spacing variation? And in the other one, do you see like wavelength variation, I would guess? That's what I'm asking. I mean, it wasn't clear for me from the pictures.
So I was just discussing with the team yesterday, and we did. I don't think we fully understand. So where's this? I don't think we fully understand what these patterns are telling us, right? It's in the literature there is a reference to ferromagnetic, antiferromagnetic, and so on. But I was trying to understand intuitively what does that mean? Why do neighboring atoms? Why are they more likely to have decayed or less likely to have decayed in these two situations? So this is something. These patterns are certainly very interesting, but we don't understand yet what they really tell us. Another thing that we would like to try is not just measure these populations, right? But you can actually rotate your spin bases before that, and then you can also measure whether neighboring emitters are in phase or out of phase, for example, right? And so together, that's what I meant earlier, that you can do this tomography and really, like, not just look at these populations, but also look at the spin-spin correlation function in not just in Z, but also in X and Y or so, right? I think then you could really that would be really interesting to see these, for example, these dark states with entanglement, yada yada. You could probably measure some really interesting things there. But yeah, so we are eager to learn more about what we should do there.
Thanks.
Hi, thanks so much for the fantastic talk. I have maybe two questions. One is about this slide. Can I understand this? So if I look at the, somehow in the super radiance part, when you have this ferromagnetic correlation, there seem to be many atoms that are like positively correlated with the central atom, and then towards the edge is the opposite. Can I understand this as the fact that somehow this dissipative interaction between the atom changes sign, and that's over the several lattice sites, and that's why there is this anti-correlation, at least at the early super radiance?
What sign change are you referring to? You mean the outside is blue here, or?
Yes, yes.
So
I'm imagining.
So I think in the experiment, I think it's just noise, and here I think it's just conserved number or something. So if you have more in the center, you have less on the outside. Is my understanding.
Okay.
So I'm not so sure about the sign change there, but the market sign change that we just realized we don't really intuitively understand quite yet is the one as you go from super radiance to sub radiance, you have this fairly sudden change in correlations.
Okay, thank you.
Thanks for a nice talk. So got a question about the same slide. Just to make sure I'm not missing something, when you say spatial autocorrelations, it's actually spatial correlations. I mean, what do you say, autocorrelation?
Correlation. Spatial. Spatial correlation. Yeah. I mean, what we just do is, right, like if one atom is in the upstate.
What are the neighbors?
what is the probability of the surrounding ones to be up or down, right? And that just averaged over all positions, yeah.
So there are two things that you showed. One is that the effect gets stronger as the system gets bigger, and these correlations are very short range. Right, so there seem to be two different things going on. And I was wondering whether, if you look at a spatial resolved pattern, whether you've perhaps got small bubbles, like in this pattern growing, which then with time perhaps overlap in a way that what you're left with is then the blue patterns for the bits which haven't been, which haven't decayed yet, as it were.
I mean, I wouldn't say it's that small, right? It's a good fraction of the system size. Like here you have whatever, like radius 8 or something like that, right? Again, if you were to measure in the spin base in the XY direction or so, I mean, in a way, I'm surprised there's so much correlation in the population. Anyways, I would expect more in the spin direction. So that's definitely something we have to explore.
Okay.
And
yes, I was just wondering whether you've got some sort of coarsening process or something like this, which which gives you a crossover between the two regimes, which is some geometric component.
I mean, we're really at the very beginning of learning these things, essentially. And so, in general, because I unfortunately can't be on the conference or so, please email me if you have, like if you want to discuss, or we can meet on Zoom with, also with the team, and that would be wonderful.
Okay, thanks.
Okay, and on that note, let's thank Markus again.